quadratic forms.
Oh, quadratic forms.
So I'd like to thank the organizers for this invitation to give the talk. And so I'll continue where I left in my last talk. Okay, so maybe I was talking without taking a breath, non-stop. Maybe I'll just give some breaks this time. So, so let me just start with an invariant associated to fields which reflect the structure of quadratic forms over the field. This is called the u-invariant of quadratic forms of a field. So I'm just going to assume that characteristic of a field is not 2. So the u-invariant of a field K is simply the maximum, if such a maximum exists, of dimensions of anisotropic quadratic forms over anisotropic quadratic forms over K. So a form is isotropic if it represents 0 non-trivially. In other words, there is a non-zero vector V in the underlying space such that QV is 0. It is anisotropic if it doesn't represent 0 non-trivially. And then you just run it over all the quadratic forms which are anisotropic over the field and take the dimension of these spaces. We have defined the dimension. So the maximum dimension is called the u-invariant of the field. Of course, it is said to be infinite if there is no finite integer with this property. Okay, we'll be looking at only fields. There is a different notion of u-invariant in case the field has orderings. If suppose a field has orderings, then you take sums of squares, they are never going to represent 0 non-trivially. So the u-invariant is essentially going to be infinite, but that's not a good definition in the case when the field has orderings. But we'll stick to this because most of the fields we look at do not have orderings. Already there are interesting questions over there. Okay, so some examples. So u-invariant of course, complex numbers is 1, and if you take a finite field, this is just 2, and if you take a p-adic field, every 5-dimensional form has a non-trivial 0, and the same thing can be said if K is a totally imaginary number field. We have Hasse-Minkowski in number field. Then because of the local data, you will have that u-invariant is just 4. Every 5-dimensional quadratic form over such fields indeed has a non-trivial 0. And you have a class of fields for which you can say what the invariant, whether there's bounded u-invariant. These are the so-called CI fields. What are CI fields? So CI fields are the fields for which, suppose you take a homogeneous form in n variables of degree d with n exceeding d to the power I. The number of variables is large with respect to the degree, and this I, then the homogeneous form represents 0 non-trivially. This is the notion of CI fields. Of course, if K is a CI field, then of course if you take quadratic forms or homogeneous forms are degree 2, therefore the u-invariant of K is at most 2 to the I. Every form in 2 power I plus 1 variables, quadratic form, has a non-trivial 0. But for instance, you can take with C, and you can take function field in n variable over C. This is a Cn field, and you can also start with a finite field, and you take you can also take function fields. This is a Cn plus 1 field. So all these fields have they are CI fields, examples of CI fields. Therefore, they have finite u-invariants. However, the most tantalizing question, open question today, so you just take, so one would like to pass like this, starting from some base fields which are interesting, one would like to pass on to function fields and ask whether you can bound the u-invariant. But if the base field is not CI, then you cannot have such a nice conclusion. The typical example is you can take a p-adic field, for instance. It is not CI or C2, and similarly you can take totally imaginary number fields, which is a more global situation. In all these cases, I mean, at least in some cases we have answers. So let me just say The open question is, so K is Q root minus 1. Take this number field without ordering, Q root minus 1 is the U invariant of KT. You take rational function field in one variable or Q root minus 1. This is the first question. That is, if you take this field, whether KT, whether you can say that you can find an integer n, however large, such that if your quadratic form has bigger than that many number of variables, it represents 0 non-trivially. Okay, this is the question. One does not know an answer to this question, whether there is a finite n or you may have anisotropic forms in very big dimensions. We do not have an answer. The question is absolutely down to earth simple. And of course, we can always also ask more ambitious questions. So is the U invariant of KT 8? Because we know there are 8-dimensional anisotropic forms. Is every 9-dimensional quadratic form, does it represent 0 non-trivially? This is a stronger question. Why ask this question when you already have this open? Okay, it is just curiosity, and it is also motivated by the following situation with respect to when you replace Q by its local completions. Okay, there we have somewhat satisfactory answers. So suppose if you take
Is your scarf a necessary part?
Pardon?
Is your scarf a necessary part?
Okay. Okay, so let us take a p-adic field, QP, or you can take finite extensions of a p-adic field, and you can take a function field in one variable. So let me say Kx, where K is a p-adic field, and X is a curve over K. So in this case, you can ask the same question, whether whether the U invariant of this field is finite, even before going to number fields. So this is the first curiosity. In this case, I mean, it is surprisingly, the first answer came only in 2007, okay? And the first finiteness questions started arriving in 1997, where one knew it was finite, but one didn't have a precise estimate whether it was 8. And as late as 2007, it was proved that U invariant of KT is exactly 8. So I would just say this is a joint paper with Suresh, first when the p-adic field is non-dyadic, and then subsequently, I mean, we used, I'll tell you what methods we used, but subsequently Heath, Brown and Leap, with using completely different techniques, they proved that for all primes P, there is no distinction of the dyadic and non-dyadic. They proved that the U invariant of the field is indeed 8. So this is the motivation for asking the question for a corresponding totally imaginary number field, whether the U invariant is just 8 or every 9-dimensional form has a non-trivial 0. Okay, in fact, I've given this expository talk several times, and the question was always, if it is not 8, what number could it be? And so then you should believe it is infinite in this case. Okay, let's see how far we go. I mean, still it's open. I don't have an answer to this question, but let me just connect the question of finiteness of the U invariant to questions on Galois cohomology, because we just saw that the quadratic forms are completely classified by Galois cohomology invariance. So what does it mean the U invariant is finite? Can you translate it in terms of some things about the Galois cohomology groups of the field? Okay, this is
K of x is there, or
K of x. Here it is, yeah. Function field in one variable over x. Exactly. Okay, so I'm just going to link the two questions. I mean, translate the question of U invariant finiteness to a question on Galois cohomology. Okay, so we have this in Hn of any field K, Z mod, call this L, Z mod to Z. So you have these special elements which are cup products of elements from H1 N, where A is in L star and the class of A is in H1 L Z mod to Z. Okay, so you have this such cup products. These are very simple elements here. These elements are called symbols. I'm just going to call them symbols. And the consequence of Vygotsky's theorem that either Kn maps onto Hn or the In maps onto Hn, all of them give that Hn is generated by symbols. Is generated by symbols. Okay, so but what matters for us is how efficiently they are generated is the question. So let me say the following equivalence statement that u invariant of L, a field is finite if and only if, if, I'll just say it is in fact true if and only if, but I'll just say to start with, if the Galois cohomology groups vanish beyond a certain level. So all the Galois cohomologies should vanish, and secondly, there exists n, which may be ni, depending on I, such that every psi in hi L z mod to z is a sum of at most ni symbols. At most ni symbols. So in this case, we say that the I symbol length is bounded by ni. So the symbol lengths have to be bounded in the cohomology wherever it doesn't vanish, and together with the cohomology vanishing beyond a certain level, this gives u invariant is finite. This is once you grant Orlov, Wyshik, Vygotsky, the quadratic form version of Milnor conjecture. This is not hard. This is a non-trivial theorem, but if you grant it, this is not hard to see, because you take a start with a quadratic form, looking at its invariance in H naught, you can and then in H1 and so on. You cannot go on because then the successive invariants are only defined on In, as I mentioned it. But if you take an element of In or Hn, it is a sum of symbols. If it is a sum of bounded number of symbols, then you have a witness quadratic form of bounded dimension, which maps on to that element in Hn. Namely, you can take sum of histoforms, which map on to sum of symbols. And if the number of symbols is finite, the number of histoforms you need is finite. So by subtracting out such forms of bounded dimension, you can bring it into high filtration and then use the classification theorem, because Hn vanishes beyond a certain level. So you do get a bound on the dimension of quadratic forms over a field up to planes. Okay, so this is non-trivial, but using this is not hard to see. But suppose you want to prove finiteness of the u invariant using this, one question is, are we asking for too much because this, or is it essential to do this bounding of symbol lengths? In fact, it's also if and only if is also true. Okay, of course it's quite not obvious why it is true. The first condition is clear, because if the u invariant is some finite, and suppose u invariant of L is less than 2 to the power m for some m, okay, then every m-fold histoform represents 0 non-trivially, and the property of histoforms, it is completely split, and therefore every m symbol is split. Okay, so you will see using this that this condition is essential, that the cohomologies should vanish beyond a level is essential for the u invariant to be finite. But this is not at all obvious, and I think this is a theorem of Saltman. He proves, in fact, that this condition is also necessary to conclude that the u invariant is finite. So we have a complete set of conditions to tackle this question, whether u invariant of q root minus 1t is 8, or whether it's finite, and so on. Yeah.
Does it have to be a power of 2?
No, that's actually a fantastic examples of Mercury. It was a question for a very long time, because the so-called level of a field and so on, other invariants, they are all powers of 2. One believed, even Kaplansky asked in a paper, is the u invariant always a power of 2? And Mercury, that also in the 90s, he came up with these beautiful examples of fields with even u invariance for all even integers. 6 was the beginning. So okay, so you get u invariants which are any even integer, and even 9 is a u invariant of a field. Even odd integers can occur as u invariants. Okay, so but we don't expect such crazy u-invariants in the case of such nice fields. That's the point. Okay, so let us come back to this question. What do we know? Suppose K is a totally imaginary number field. Imaginary, that is field without ordering, number field. Let us stick to this notation, x over k, smooth, because I'll use this later, smooth projective, geometrically integral curve. You can always reduce to this, and capital K is the function field of. So we are interested in the u-invariant of this field. So to start with, first of all, the so-called cohomological dimension of this field is 3. That means we define the Galois cohomology groups. If all torsion Galois cohomology vanishes beyond a certain level, you say that the cohomological dimension is bounded by that number. Here we are basically interested in Z mod 2. So the cohomological dimension of this field is 3. All Hn, the Galois group of K with values in any finite torsion is 0, n greater than or equal to 3m torsion Galois modules. So all the Galois cohomologies vanish beyond the level 2, level 4. H4 is 0. Okay. These fields have H4 onwards, or Hn is 0 for n greater than or equal to 4. So very nice. So we have to prove symbol length for only two groups, namely H2 and H3. It should not be too bad. So let us see what it means. So u-invariant of K of x is finite if and only if symbol lengths in H2 and H3 are bounded. So this is a necessary and sufficient condition for the u-invariant to be finite. So here, in fact, I want to just draw the parallel with p-adic fields. How was it proved that the u-invariant was finite to start with, or it is 8 eventually? Exactly, one followed the same pattern. So one tried to analyze the 2 symbol length and the 3 symbol length in that case. In fact, we had the following results in the p-adic case. So now it is K is QPT or any curve. In this case, we proved that everything in H3 is a symbol. Okay? So I should state it after stating something about the Brauer group. So everything in H3 is a symbol. In fact, I want to make this remark because we are eventually hitting at whether the u-invariant of the field could be 8 instead of even finite. It is a fact that if the u-invariant is 8 or less than or equal to 8, everything in H3 has to be a symbol. This is a necessary condition for the u-invariant to be bounded by 8. So this we proved after the following, which was something about the Brauer group. This was proved by Saltman, that everything in H2 is a sum of 2 symbols, at most 2 symbols. So the symbol length for H2 is 2, symbol length for H3 is 1, and therefore you get immediately some rough bound like u-invariant is at most 16 or something. This bound, or even 12, was obtained in 97, but it took 10 more years to arrive at exactly the number 8 for the u-invariant. Okay, and so this is exactly the pattern in which the local case was handled. Okay, so here what do we know in the case of function number fields? So I just want to state the following theorem.
Yeah, conjectural dimension is 3, means that the Hn is 0 point greater than 3?
Yeah, greater than or equal to 4.
Okay.
At least 4. The cohomological dimension means beyond this the cohomology groups, thank you. Beyond that level the cohomology groups vanish. Okay, this theorem is really, this is just hot from the oven, and this really makes one once again feel possibly it is true that the u-invariant is 8. So this is the amazing fact which Suresh proves, that if K is a totally imaginary number field, and same notation, function field in one variable over K, function field in one variable, then 3 symbol length is 1. That is, every element in H3 is a symbol. So this is a real leap in this direction because we didn't know this, but we had a way of getting around H3 to come down to H2 in some other way. But this really says that everything is a symbol, which is a necessary condition if ever you eventually prove u-invariant is 8. So this is a real positive step in this direction, which gives hope that probably one has some positive results. Okay. Now comes the question of H2. So symbol lengths in H2. So we have said already H2 is nothing but the 2 torsion of the Brauer group of K. And in fact, the Milnor conjecture solution due to Mercurius says that every element in the 2 torsion of the Brauer group is a sum of symbols is the same as it is a tensor product, is Brauer equivalent to a tensor product of quaternion algebras. Quaternion algebra is the building block for the 2 torsion of the Brauer group. Okay, you have to bound the symbol length, and here I want to make the following simplification. So symbol length is bounded for H2 is the same as this is the same as you can interpret it as the indices are bounded for central simple algebras. Central simple algebras over the field K. We said every central simple algebra is like matrix algebra over a division algebra over the field. The index is just the square root of the dimension of D, which is an invariant of the Brauer class. So this is the index of this thing. And you can see immediately if you have symbol length is bounded, you have some finite product of quaternion algebras. Suppose it is R-fold tensor product of quaternion algebras, then definitely there is an extension of degree 2 to the R which splits it. So the index is at most divides 2 to the R. This way is easy, but the other way is also not difficult to see. I leave it as an exercise. You use the construction of the Brauer-Savary variety or the function field of a Brauer-Savary variety, generic algebra, to determine there is a symbol length in this case, which is finite. Okay, so basically we can convert the problem of bounding symbol length to bounding the indices of central simple algebras. Okay, so in this case, I just want to have an auxiliary. We go on till what time? Oh, okay. I don't have to rush. Okay, so in order to, I just need to introduce the notion of ramification of Brauer classes. So ramification. Okay, this is, suppose L is a discrete valued field with discrete valuation V, O is integers, the valuation ring in L, and suppose kappa is the residue field. I may not use all, and suppose pi is the parameter, the uniformizer. In this case, you say that any alpha in the Brauer group of L is unramified on O at the discrete valuation. You say it is unramified if it belongs to, if alpha belongs to the image of the Brauer group of O to Brauer group of L. The image of this map from the Brauer group of the local discrete valuation to the Brauer group of the functional field is in the image. You say it is unramified at the discrete valuation. And we have the situation of a curve over a number field. Let me take the ring of full ring of integers in K, and let me take a regular model for this x over K, x to O, regular model for x over K. For this curve over K, let me choose a regular model. Then we the Brauer group of K of x, which is unramified on the model. The Brauer group unramified on the model is simply the set of alpha in the Brauer group of K of x, which is unramified at every discrete valuation at Vx, every discrete valuation of the function field, which is centered on codimension 1 points of this. This is a two-dimensional. The regular model is a two-dimensional scheme, which is a relative curve over the integers. You take codimension 1 points of this, and you take the local ring, that's the discrete valuation ring. You have the associated discrete valuation. At each one of these discrete valuations, if it comes from the integers, some kind of purity will give that in fact it comes from a Brauer class on the model. Then you say it is unramified on the whole model. Okay, this is the notion of unramified Brauer group. Okay, so if you want to, okay, what are we interested in? We are interested in bounding the indices of central simple algebras. That means given a Brauer class, you want to split it in a bounded degree extension. If you want to split it in a bounded degree extension, maybe you attempt first to make it unramified on a suitable model in a finite degree extension. That is the first step. And then see if you have something unramified on a model, whether you can further split it in a finite degree extension, bounded degree extension. These are the two steps involved. And let us see step, so there are two problems. One, can one are the indices, okay, maybe can one split the ramification? One split the ramification I will just not write again. We are having this fixed situation. You can fix a model. And the first question is whether one can split the ramification of Brauer classes in a bounded degree extension. So it doesn't depend on the given Brauer class. If you can have a bounded degree extension which splits the ramification, this is the first question. And I will tell you motivation for this question because of history. And secondly, can one bound the indices of unramified classes? Indices of unramified Brauer classes. Unramified on a model, I mean. Unramified means always on a model classes, Brauer classes. Everything is concerning two torsion. There are two things we need to analyze, whether you can split the ramification in a bounded degree extension, and secondly, whether if you already have an unramified Brauer class, whether you can split the class in a bounded degree extension. So in fact, this is exactly how the local field case was settled. In fact, let me just indicate how Saltman's proof in the case when K is a local field now instead of number field. How does he achieve? He proves the following. Everything is the sum of two symbols which I said for mod 2 and so on. How does he go about it? He just says that suppose alpha in the he doesn't talk about two torsion or anything, any p torsion, whatever it is, and assume p through, or it doesn't matter, let me stick to two torsion. What he does is that, so there exists fg, two functions in k of x star, such that when you go to the square roots, this biquadratic extension, kx, root f, root g. So let us go to this biquadratic. You can choose functions which depend on alpha, but the degree of this extension is 4. When you go to this extension, it is unramified on a suitable model for this curve. On a suitable model suitable model means model over integers of this curve kx square root f square root g. This is what he does. And of course, in this case, K is a p-adic field. P is not 2 is needed for him because in order to split ramification, there are certain, I said the class is unramified, it comes from the discrete valuation ring, but there are certain test maps which map from H2 to H1 of the residue field, which are defined only in the case when the residue field characteristic is not 2. So splitting the ramification very much uses, the Saltman method uses that the residue field characteristic is not 2, and then he then just by looking at the residue maps and so on, arranging these functions suitably, he proves that the ramification can be split. Okay, this is a doable thing, splitting ramification. Of course, it was doable once Saltman says how you do it. Okay, so we know how to split the ramification. Okay, but here the story ends in the p-adic case for splitting classes, because once it is unramified, you have a model Y over the corresponding ring of integers. This is a two-dimensional regular scheme proper over a complete DVR with residue field a finite field. So there is no Brauer group for Y. Once it becomes unramified, it comes from a Brauer class here. The Brauer group of the scheme is 0 in the local case. And it finishes the proof that the index is bounded or the symbol length is bounded. Everything is finished at this stage once you split the ramification of the Brauer class. Okay, but here, okay, so here suppose you want to do a similar thing in order to split the ramification. Okay, you have to take care of dyadic primes. Okay, so you cannot avoid the residue field characteristic not 2, and we cannot assume this, because when you have ring of integers in a number field, you always come across dyadic primes, and then it's subtler to see how to split the ramification at dyadic primes as well. Okay, so this has been done actually. There is a paper, whatever I am going to describe now is in a paper which was written jointly with Max Lieblich and Suresh. So the theorem says that you can split the ramification. It has been done. So there exists FGH. Now instead of 2 functions, we need 3 functions to take care of also dyadics, such that, given alpha, given a Brauer class alpha in the 2 torsion of the Brauer group of the function field Kx. Now K is a number field here. We are coming back to number field case, and also we are assuming no ordering. This is the standard assumption. Here we prove that there are 3 functions such that alpha is unramified when you go to this square roots of this on a model of this field Kx square root f square root g square root h. Okay, so this is the first step, and this already involves somehow delicate handling of dyadic primes. This has been done. So the first step of splitting the ramification in a bounded degree extension is done. So the only thing left is just to deal with unramified classes. Okay, so whether suppose you have a number field and a ring of integers, a number field without ordering, a number of integers, and you have a smooth curve over K, and you have a model over the integers, and you have a Brauer class on the model, whether you can split it over the function field in a bounded degree extension. The whole question reduces to this particular statement, whether you can bound indices of unramified classes. So at this point, I just want to say there is no answer, it is not known. However, there is a conditional result. So to explain this conditional result, I just need to explain what is the Brauer-Manin obstruction. So let me state the theorem, the conjecture of Colliot-Thélène. I'll explain the terms here. Conjecture due to Colliot-Thélène. So a K is a number field, X over K is a number field. X over K is a smooth projective, you can assume however nice it is, projective geometrically integral variety over K. Then the Brauer-Manin obstruction is the only obstruction to existence of 0 cycles of degree 1, existence of 0 cycles of degree 1 on X. Okay, I don't know, maybe one of you has an example to show this conjecture is false. Maybe people don't completely believe in this conjecture, but let me just explain the terms in this statement of the conjecture. No, here, I mean, there is no, I mean, I think you expect this cannot be true in general, but nobody has constructed an example. First of all, I want to say that a similar statement, when you replace zero circle of degree 1 by rational points, whether the Brauer-Manin is the only abstraction, is there are examples of varieties for which Brauer-Manin is not the only abstraction, even though it's not very, very, very long ago. It was pretty recent due to Skorobogato to start with. Now one understands this phenomenon better. So for rational points, certainly Brauer-Manin is not the only abstraction in general. However, for zero cycles of degree 1, even non-rational, I don't think anybody has, should be possible. But however, the conjecture we want to use in the setting when the variety is unirational. Okay, they are nice varieties. So perhaps even if this conjecture is not true, in general for the situation we need it, there is a possibility the conjecture may be true. So let me just explain what is the Brauer-Manin abstraction. So you have the set of rational points of K, and you have the local, suppose the Brauer is the only abstraction to Hasse principle, I should say, to Hasse principle. For Hasse principle, always you have a variety over a number field, you assume things, nice things happen over the local, over the completions, and you want to know whether the nice things happen over the number field. This is the kind of Hasse principle questions. So if you have a number, you have a variety over number field, you have the K rational points. Suppose the variety admits local points for all V. So I'll take product, I'll assume X over K is proper, and then you have these two, and in between is called a set which is called the Brauer-Manin set, which can be described as this is the set of all local points ZV in product XKV such that V in omega K, such that for every alpha in the Brauer group of X, so you can restrict it to ZV, you get a Brauer class in the local field, and then you can take invariance of the Brauer class and sum it over. This is a finite sum, this should be 0. So you just specialize the Brauer class at the local points and take the invariant and sum it up. This summation should be 0, that is the condition of the choice of the local points. This is called the local points orthogonal to the Brauer group. This happens for every alpha in the Brauer group. So this set, Brauer-Manin set, is caught between here and here. Even though this may not be empty, if this is empty, then you will have failure of Hasse principle. Okay, we can define the Brauer-Manin expression for zero cycles of degree 1 as well, because instead of specializing at rational points, you can specialize at zero cycles of degree 1. You'll have a summation of invariance. You can still demand it is orthogonal to the Brauer group. Then you can ask the same question whether this is the only abstraction to existence of zero cycles of degree 1. And that is Colliot-Thélène conjecture. He believes it is true. Okay, so the statement, the second theorem is also the same paper. We prove that if CT conjecture is true, then the index of unramified classes divides 4. Divides 4. It has bounded index. It is at most 4 for the unramified Brauer classes, provided we have this truth of this conjecture. And maybe the next few minutes I'll explain for which variety do we need this conjecture to conclude. How do you go from this question to the question of Colliot-Thélène conjecture and Brauer-Manin? What is the variety which enters the picture? Maybe I'll just explain quickly some kind of sketch of how this goes about. Okay, so you have an unramified Brauer class, alpha in Brauer group of Kx. Alpha is unramified on a model. On a model x to O. O is the integers. So we have a class which is unramified on a model. And this is, so I'm going to take something in the 2 torsion. So first of all, I can lift it to something in H2 of x with values in mu2. This maps onto this alpha in H2 K or Kx mu 2, which is the two torsion of the Brauer. I can lift it all the way to H2 X mu 2. This is the ethyl cohomology of X with values in mu 2. So because the H2 suggests onto the two torsion of the Brauer group, so you can lift it to a class alpha tilde here. And this can be interpreted as a mu 2 gerb. This alpha tilde, you can think of it as a mu 2 gerb. And we will restrict it to the curve itself, which is more geometric. The restriction of alpha tilde to the curve, this is again a mu 2 gerb over X. For the curve instead of the model, let us look at this mu 2 gerb. In the case of a curve and given a mu 2 gerb, then Lieblich constructs this moduli space. So the moduli stack, M is the moduli stack of rank 2 locally free stable sheaves of trivial determinant, say trivial determinant. So this is the usual moduli space, moduli stack of this X tilde twisted. Now instead of taking usual moduli space, you just take this mu 2 gerb twisted bundles of rank 2 and trivial determinant. So this is the stack, and you have the associate. All this is constructed by Lieblich in his paper. This is the associated moduli space of exactly rank 2 locally free stable sheaves of with trivial determinant. So this is the moduli space, and this is the moduli stack. And this moduli space is the space. Of course, this is not. This is quasi-projective, and it is smooth, but it is not projective. So you can just take for the applying Colliot-Thélène conjecture, you can take to be some smooth compactification, whatever compactification you like. For this moduli space, these are the spaces for which the Colliot-Thélène conjecture is needed to conclude the indices are bounded. Okay, but we can say that these moduli, this twisted moduli spaces, when you go up to the algebraic closure, they actually become just moduli spaces. Okay, they get untwisted. You get the usual moduli spaces of rank 2 vector bundles, stable bundles with the determinant. There will be a twist which will give rise to a given determinant. So these become actual moduli spaces, which are all, say, unirational varieties or whatever. So you expect probably the conjecture is true for such varieties. Maybe I'll just say a few words about how this, given this fact for these moduli spaces, that if they locally have 0 circles of degree 1, they have a 0 circle of degree 1, leads to indices being bounded. That is the question. We are bounding indices of algebras. So let me quickly run over how the index of algebras enters the picture. So given this moduli space, okay, suppose what does it mean that it has a rational point? So let us understand what does it mean that this moduli space has a rational point. This means suppose you take a rational point in Mk. Then, so did I mention that the moduli stack? So you have this moduli stack and the moduli space, and this itself is a mu 2 gerb. The moduli stack over the moduli space is a mu 2 gerb. So when you just restrict this to the point, the moduli stack to this the point x. So this is a mu 2 gerb over a field, and what is the kappa x? The field is just a number field, correct? This is k itself, it is a rational point. So you get the restricted to this point x is a gerb over mu 2 gerb over k, which is a number field. So mu 2 gerb over a number field, these are classified by H2k mu 2. And this is the two torsion of the Brauer group. Any element here can be split in a quadratic extension L over k. Any Brauer class which is two torsion, the index is exponent for algebras over number fields. So if you have a 2 torsion element, you can split it in a degree 2 extension, which means that this job is trivial when you go to L, which means that the moduli stack M has a rational point over this field extension, this quadratic extension. What does it mean? The moduli stack classifies rank 2 twisted sheaves. Suppose E is the rank 2, E over L is a rank 2 twisted sheaf, X tilde twisted sheaf, X tilde L twisted sheaf. Because the stack is not empty means that there is a rank 2 stable, etc., etc. There is a point on the stack, which means, and then once you have a rank 2 twisted sheaf, then you can check that the endomorphism of this rank 2 twisted sheaf, the class of this is nothing but the Brauer class you started with over the function field. This is how the generic construction goes. So you have this endomorphism of E is a rank 2 bundle. Whatever it is a degree 2 algebra. Literally you get a degree 2 algebra, which means that index alpha is 2. Which means that alpha index over L of alpha is Lx is 2. That means alpha is split in a quadratic extension of, once you have got a degree 2, you have bounded the index, quadratic extension of Lx. Already we have gone to a quadratic extension of little k, this is degree 2, kx over Lx. And then one more further extension, Lx root f. You have to go one more further quadratic extension to split this index 2 algebra. So you have split the algebra in a degree 4 extension. Okay. Now, I mean, the same proof works also. You don't really need a rational point, because indices, if you have index, you compute the index in coprime degree algebra extensions of algebra, then you know the index below. Okay. This is because it's defined by cohomology. So it is enough that same conclusion if M admits a 0, instead of rational point, you can enough to admits a 0 cycle of degree 1. You can do the same thing and you arrive at the same conclusion that the index divides 4, even if it admits a 0 cycle of degree 1. So, but why? I mean, how are we going to use Colliot-Thélène conjecture? In fact, it is true that MKV is not empty for all V. The space locally admits a point. Why is this true that it admits a point? Locally, what does it mean? This means that, first of all, let us look at the situation. You have an alpha in the Brauer group of the model. This is where we use that you have something on the model. So when you go locally, the Brauer group of the model is 0. So the H2 element, when you go to the 2 torsion of the Brauer group of KV of X, is 0. Alpha V is 0. When you take the Brauer class and look at it locally, the Brauer class is 0. Once the Brauer class is 0, you have a line bundle, twisted line bundle. This is exactly what it means that the Brauer class is 0. It's called essentially trivial. You have a twisted line bundle on X. Once you have a twisted line bundle, you can use this twist to untwist the moduli space itself. So the moduli space actually becomes isomorphic to the usual moduli space, because this twisted line bundle, when you take square, it becomes actually an untwisted line bundle. Let me call it L inverse. Then the moduli space is simply the twisted moduli space is simply the moduli space of rank 2 stable ... locally free sheaves. And now, though we started with the twisted rank 2 bundles with trivial determinant, here it becomes determinant equal to this specific L, which comes with the twist, the square of it is determined up to squares. So this becomes the usual moduli space of rank 2 stable bundles with a specific determinant, and we are in a characteristic 0 field. There is always a rank 2 bundle with whatever determinant prescribed, which is even stable. You can always produce such a bundle. Therefore, this moduli space is never empty, the usual moduli space. Not empty, it has a rational point. Therefore, This twisted moduli space also locally has a rational point. Of course, you can pass from, maybe you all can do it better than me, from the moduli space to a smooth compactification. You can just do some moving the cycles, so you can go back and forth. So this is the reduction, how we arrive at indices dividing 4 for unramified classes, provided you have such a general statement true for a local global principle for 0 cycles of degree 1 on smooth projective varieties over a number field. So I'll stop here.
Thank you for a very inspiring talk. Question.
So just to clarify, that last step was how you're showing the Brauer mandate set is non-empty.
Oh, that is the point. Okay, I just missed it. It's not enough that it has a local point. But basically, the Brauer group is just Z mod 2, generated by the job m tilde to m. And you can show that any choice of local points, this is going to vanish. So it is in the Brauer-Manin set. Yeah. Yeah, of course, I just missed the point. Yeah.
Ramified Brauer class on a regular arithmetic surface like that, and then you invert 2. Do we have a period index bound?
It is not that simple. If you have, then you will have over the function. So it is far from clear now. Yeah.
Is it easier when the curves are hyperelliptic?
I have been working with one of my colleagues in India, Jaya Iyer, because she comes in the moduli space front and then knows moduli spaces very well. We have been working for now a bit of time, but we haven't reached the end. Hopefully, yeah. And already it will be a good step, because maybe the curves which we come across, or you can start with qt, even to prove u-invariant finite for q root minus 1t rational function field, you will go to extensions like root f, root g, root h. Basically, it is some kind of a join of hyperelliptic curves. Maybe there is a way to come back to general curves, but hyperelliptic one needs to know first. And we have been working on it, probably, I'm not sure. I don't want to commit to anything.
Other questions? Here again, we'll meet here. Some people will meet here again at 2 for the free talk, and then everybody else at 2:30. Right? So thank you.